Hello, good evening. Good evening. I am Abhinav. I am a PhD student at ISC Bangalore in the Department of Materials Engineering. I will be the teaching assistant for this course, Mechanical Behavior of Materials, which is being hosted on NPTEL, and it is being taught by Professor Sankaran from IIT Madras. This is the fifth week of the doubt discussion session. Hmm. So, in case you have any doubts, you can unmute and ask me anytime, even now. Uh, Otherwise, we'll start with the session. So initially, I'll summarize and highlight the key concepts which were taught in week 5. And after that, we'll look at assignments, at the assignment questions of previous year, which will be on the week 5 content. So in this, some of the last portions of week 5 content will not be covered because I could not get the time to look at it. So I'll cover them in the subsequent session along with week 6. Some of the uh, last portions of week 5 will also be covered. So let us now start with looking at some of the concepts and topics which were covered in week 5. We had already looked at dislocations in the previous weeks. So different characters of dislocations, the phenomena involved with dislocations, their how they are connected to a strain, how they are involved in the plastic deformation of a material. So we have looked at all of that. So in this, we'll continue with that by looking at dislocations which occur in ordered crystal, also called super lattices, because you have two different lattices which are meshed into each other. So this is common in many alloys. For example, many BCC alloys have B2 ordered lattices. So B2 basically is uh, two different simple cubic structures which are um, meshed into each other such that overall they seem to form a BCC like lattice, but they are ordered. So every atom has a specific spot which it will occupy. It will not occupy the position of a different element. Similarly, we have L12 structure, which is FCC like, and it is the most popular or common L12 structured alloy is the nickel based super alloy, which use in which the gamma prime phase is L12 ordered, and it helps in improving the high temperature strength of the material. So in these ordered lattices or ordered phases, the dislocations have somewhat different characteristics. So in these cases, it's possible that if a single dislocation moves through, it can form antiphase boundaries. So because you have two or more different element atoms in super lattice or ordered phase, in case two different, if in case the elements of the same type come together, because that is less favorable. elements of two different types together, for example, AB is has a lower energy than AA, which corresponds to like elements coming together. So in case AA is coming together, sir has shown it in his video. So in that case, the energy will increase, and that kind of boundary is called the antiphase boundary, where AA is forming, and the energy is almost equivalent to that of stacking faults. So this is also a kind of fault only, because locally there's a boundary getting created which has a higher energy. So in such cases, instead of single dislocations, superlattice dislocations exist, which basically are two or more dislocations which move together in the ordered phase, so that the overall energy is lesser than what it will be for separate dislocations. Basically, the idea is that if you have two dislocations, it will form less of APBs compared to just one dislocation. But since dislocations will repel each other, they will also split. So there will be equilibrium separation at which the two dislocations will be at. And because of that equilibrium separation, for example, in case of what we see in case of partial, that will happen. So dislocations will split into partials, as well as the dislocations will have a separation between each other too. So what will happen is that here you will have, let me show in this notes, a stacking fault getting created. Yeah, here you will have a stacking fault getting created because the dislocation have split into partials, and between the two partials we have the stacking fault, as we saw in is the case in FCC material. This is for L12, and in between the two dislocations which split into partial, there will be a APB forming. So it's this region. So the equilibrium separation will depend on the energy, stacking fault energies, APB energy, but we'll have this kind of situation. Hmm. And because antiphase boundary is forming, which is associated with higher energy, the general observation is that this leads to an increase in the strength, because dislocations, uh, the movement of dislocations in the ordered phase is more difficult since APBs are forming compared to that in a just random lattice which has no ordering, which can be called a matrix phase. So because of this ordering and APB generation, the dislocation motion is difficult, and as a result the strength is higher. So in case we have a ordering transition in any alloy such as nickel based superalloy, that will be associated with an increase in the yield stress, and this phenomena is also called yield stress anomaly for Ni based superalloys. And in these alloys, half 110, which is the lattice translation for FCC, will not be an actual lattice translation, because that will lead to a change in the neighborhood of the elemental atoms, of the elements, because AB will might become AA afterwards. So there is a change. It's not a lattice translation. Also, another just point is that the APB energy is lower on certain planes compared to others, because of how the sharing is taking place, or what are the new bonds which are formed. Based on their nature, the APB energy will be decided. So for 100, it has been seen to be lower, but it's also known that 110 is more close packed and more efficient for slipping compared to 100. So pulse stress for 100 is higher. As a result, due to this phenomena, we see that kind of lock forms, which makes it difficult for dislocations to move. Even though APBs are more favorable in 100, the mobility is lower. So Kier Wilsdorf lock forms in such cases. and these locks can lead to strengthening and work hardening. We'll see what how that happens in the subsequent points. So the this was all about mm, introduction to dislocations and looking at some fundamental things which are involved in plastic deformation. Till now, we did not touch plastic deformation like in general. We just looked at some specific mechanisms or entities like dislocation or partials which contribute to plasticity. Now we'll move to plasticity. So firstly, we'll look at the failure criteria. So we have already looked at elastic deformation. In that we so in that we considered the effect of different stresses on the strain values and transformation of coordinates. But here what we look at is what is the, in case plastic deformation, we are in the plastic deformation regime, that is higher strain values, then for what stresses can we expect yielding of material to happen. So basically we want to have some criteria to predict whether yielding or failure will occur, so that we can design our components accordingly based on what are the conditions that will be experienced for any loading application. Hmm. So when we want to do that, when we want to be able to predict whether for a particular stress state there will be yielding or failure or not, we know that any coordinate transformation of that stress state should not change the decision whether yielding will occur or not occur, right? Because the coordinate is just a system of referencing. It will not change what is the stresses which are actually being strains which are actually being experienced by the body, right? It's just a reference system for us to be able to quantify things and represent things. So we know that the invariance of the stress state will have a relation with the yielding or the with the criteria of yielding or failure. Failure, by failure I mean fracture. So considering this philosophy, there were multiple criterias which came up in the last 1 century. So one criteria is maximum normal stress criterion. I'll go a bit quicker since this is covered in detail in the slides. So one is the maximum normal stress criterion, where we look at what is the normal stress, what are the principal stresses for the stress field, and what is the maximum value of the principal stress in any direction. If that is more than the stress required for failure, it could be for yielding or for fracture. If it is more than that, then we say that the component will fail, and that is the threshold stress that can be applied. So, okay, when we want to compare in any criteria the stress state of a material to something which is more general or easier to compare with, it will be for uniaxial loading, because that is the easiest way to experimentally know the property of a material. You just load it in one direction uniaxially. You look at the yield stress and the UTS value, because after UTS it has failed, the material will start to the stress load taking capacity of the material will decrease, so it will naturally fail for the load which has been applied. So usually for any material, you know the properties for uniaxial loading, that is the yield stress and UTS. But now we want to compare, now we want a criteria which will compare the stresses in a more complex stress state to that which are found from a uniaxial test, so that it can be predicted whether a component made of a particular material and experiencing a particular stress state will fail or not fail. So in this case, the sigma failure might either be UTS or YS depending on what we are interested in. Now, similarly, there is also maximum shear stress yield criteria called the Tresca criteria, which is also quite popular. And since we are making use of the shear stress value here, it is more applicable for plastic deformation, that is for metals which undergo failure usually with plastic deformation. The previous was for those which undergo failure in a brittle manner due to breaking of bonds directly. So hard metals or ceramics which do not show plasticity. In this case, we look at the shear stresses on the three different planes. What are the maximum shear stresses? And the maximum one among them should be more than a particular threshold value for failure to occur. And this value will be the value which you will get if you are loading just uniaxially. And that, if you calculate, will be sigma ys by 2. So in a uniaxial tension test, the maximum shear stress is sigma ys by 2. You can very easily find that by using a Mohs circle. So this is how you compare between a complex stress state and a uniaxial loading stress state and come up with these criteria. So another criteria is the octahedral shear stress or von Mises or distortion energy criteria, where instead of looking at the stresses on the xy, xz, yz plane, you look at the stresses on the octahedral plane, specifically the shear stress, maximum shear stress on that plane, and it will come out to have this value where sigma 1, sigma 2, sigma 3 are the principal stresses, and this should be more than root 2 by 3 into sigma y uniaxial, the counterpart for the uniaxial case. And this also happens to be the condition where you have sigma equal to sigma h. So on the octahedral plane, you will have the stress, normal stress equal to hydrostatic stress. So that also kind of points out that this might be important criteria for failure, a good criteria. And it also occurs that that the energy associated with this particular stress state, this particular plane is the same as the distortion energy. So if that energy is higher than than the value you get for uniaxial, then failure can occur. So three different um, phenomena are there which involve the octahedral shear stress, which involve the octahedral plane, and that's why this is also an important criteria called, most commonly called, the von Mises criteria, and this is the most general form of it. Now when we look at the yield surface due to both of these, so here it's shown in 2D, but in 3D also you can make this. So if you just look at sigma x and sigma y which is being applied to a material, then if the value of sigma x comma sigma y is lying outside this dotted ellipse, then it will fail according to one Mises stress. While if it is outside this hexagon, it will fail according to Tresca. So Tresca is more conservative because even in the in between region, it predicts failure. This has been very well covered by sir. You can look at that. Now we okay. Mhm. We also will look briefly at yielding in polymers. So here also you have similar criteria, but there are some differences, some small differences. So one of them is that you also have a friction stress which is used here for the calculations. So along with the critical stress, you have a friction stress, critical shear stress, friction stress, and the sigma normal stress. And this is called the Mohr Coulomb model. Similarly, you also have a Tresca criteria. Okay, von Mises criteria, modified von Mises criteria. So all there, these are just modifications of the plasticity criteria in which are used in metals and brittle alloys, and just they have been modified so that they can apply for polymers. Mhm. There is some issue with the notes here. I'll have to see. Anyway, so that was for polymers. Okay, the notes have got kind of jumbled up. Let me just see once what happened here. I think some issue was there while while preparing the notes. Just give me a minute. I guess now it's okay. Just give me a minute. There was some issue in the notes. Mm. Mhm. Yeah, now let's look at it. So here, yeah, I was talking about polymers. So we have three different criteria, which are just some modifications of those which were there for the metals. Now we'll move on to looking at slip. So there are two different phenomena which majorly are responsible for plastic deformation in metals, or plastic deformations in uh, any alloy, even for some non-metals, but mostly it's either brittle or it is something like polymers which have completely different mechanisms. So one of the two mechanisms is slip, which is the most important in terms of contribution towards plastic deformation. The second is twin, which also has some amount of contribution. We look at both of them now. So all the fundamentals of dislocations which we looked at till now will now come into use, because this is connected to dislocations only. Slip basically refers to glide of a dislocation uh, on any particular plane in any direction. So that plane and direction are called slip plane and slip direction. And because the dislocation is gliding, basically there is an atomic bond switching happening, and that can be seen as a small slip occurring. And once the dislocation moves across the whole materials and reaches the surface, it comes out from the surface, and that causes a step, which is also called a slip. That's why we say that that slipping occurs due to movement of dislocation. And because it has a plane and direction associated with it, we say that it is associated with a slip system. So together we can call it a slip system. And this is nothing but just the movement of dislocations. And dislocations are the entities which are responsible for creation of the slip steps, which ultimately results in plastic deformation of the material. Hmm. Now we already know that plastic deformation happens due to shear stresses, and dislocations also move due to shear stresses only. So since we dislocation is associated with a slip system, the applied stress will not directly be experienced by the dislocation. There will be a resolved shear stress which will be experienced by the by the dislocation, based on what is the slip system of the dislocation. So that resolved shear stress can be calculated using this formula. So this is basically the effect of the geometry of the slip system with respect to the loading axis, which decides how much of resolved shear stress will be there along the slip system. Sir has already explained the derivation of this. It is simple. So here lambda and phi are angles uh, which give information about how the slip system slip plane normal and the slip direction are related to the loading axis. I won't make the geometry here, it's in the slide. So this way you can get a estimate of what will be the shear stress which will be experienced by a dislocation. Now, there can be multiple slip systems in which are active in any crystal, or which are favorable for dislocations to move on. So in FCC, the we have already seen, based on pile stresses, that the most widely spaced planes are the most favorable, have the lowest pile stress, where pile stress is the stress required for a dislocation to move. and the closest packed directions have the lowest pile stress. So the planes should be widely spaced and the directions should be closely packed for the pile stress to be lowest. So this happens to occur for 111 plane and 110 direction in case of FCC crystal. And we can have 12 such combinations of planes and directions. So we have 12 independent efficient slip systems in FCC. And there will be other slip systems on which the dislocation can move, but the stress required to move the dislocations on them will be much higher. In BCC, we do not have as efficient slip systems as we have in FCC. So, but the number of slip systems on which the dislocation experiences almost comparable stresses is more. So we have 48 slip systems in BCC which have comparable CRSS uh, or pile stress, we can say. CRSS we'll come to later. In HCP we have 12 such slip systems, but they have different pile stresses based on the C by A ratio, that is the geometry of the unit cell, because that will also affect the distance between the planes as well as direction. Just give me a minute. Yeah. Hmm. Yeah. So HCP crystals will have different pile stresses or CRSs based on the C by A ratio. So in some cases, we will see maybe later that in some cases, basal slip might be, this is basal slip, this is the basal plane. So basal slip might be more favorable, and that tends to happen for those which have higher C by A ratio, that is more widely spaced basal plane. In some cases, the prism or the prismatic face is more favorable as a slip plane. So that happens for lower C by A ratio. So usually for metals like magnesium, basal is more um, favorable, while those like zirconium or titanium, prismatic is more common. Then we have already looked at resolved shear stresses, so it can also be written in this form, where sigma y, where say, here we are looking at yielding phenomena. So if the applied shear stress, applied uniaxial stress leads to yielding, then it can be called as sigma y, yield stress. And in that case, the resolved shear stress value can be considered as a critical shear resolved shear stress, because that is the shear stress resolved shear stress value at which the material is plastically deforming. So since we know that loading above yield strength will cause plastic deformation, we can relate that to the resolved shear stress on a slip system and call it the critical resolved shear stress. Here M is just a constant which will depend on the geometry we have already seen. So it will be inverse of this, and M is also called Schmidt factor because it was given by Schmidt. This critical resolved shear stress for any slip system will vary with the temperature. So the exact variation sir has already shown. It was something like this. This temperature, this is tau CRSS, and it will also vary with the strain rate because deform strength is strain rate dependent, and it's important to keep that in mind when you are designing things. That strain rate will have an effect on how much strength your material can bear. Shock loading and creep loading will have very different effects on the material. Hmm. Now we'll come to work hardening. So the most easiest or most direct way of introducing what is work hardening is by looking at this plot. Here, here you have stress versus strain plot. And here we can see that as the strain which is being applied to a material is increasing, more and more stress is required to produce the same strain. So you could also see that as if you are doing a uniaxial test on a material, you are giving a constant strain rate. So the strain is increasing constantly with time, but the stress which is being required to cause that strain change is increasing in this manner. So this indicates that the material is getting harder and harder as you are giving more strain to it. So in a way, you can say that deforming a material is making it harder, or we can call it work hardening. We can say that work hardening is taking place in the material. And we'll look at this in more detail. So if we just look at a single crystal, because that is the simplest scenario, and that will tell you what is exactly happening. When we look at polycrystals later, there will be so many different phenomena which will be occurring at the same time that we will not be able to convolute the effects of each of them, and they will just add up. So for our more fundamental understanding, it's better to look at single crystals. So in case of single crystals, what is observed is that initially there is no hardening taking place, and this region is called stage 1. After a point, there is significant hardening which occurs. So the rate of hardening is quite high and it's somewhat linear. It is called stage 2. Then there is a dip in the hardening rate, which is called stage 3. This is for FCC crystals. And in very brief, I'll just tell what are the reasons for it. So stage 1 occurs because initially the usually alloys which are recrystallized or not so deformed. So they have comparatively fewer mobile dislocation, and there are no faults or dislocation tangles to act as obstacles to them, to the uh, movement of the mobile dislocation. So easy slip can occur initially, and because easy slip is occurring, you just need to apply the tau CRSS value, and that will cause plastic deformation to occur. But after some amount of time, slowly some obstacles start getting created, dislocations start to multiply, they tangle with each other, they form locks like the Lomer Cottrell locks we saw. Then in superlattices we saw this different lock. That is a different situation. This Kiel, what was it? Kier-Wilsdorf lock. So different kinds of locks can form. Then the dislocations start to cross slip because these obstacles have formed, and that cross slipping also leads to formation of locks or formation of sessile dislocation, because we know the edge components of dislocations cannot cross slip. So those will remain immobile while the screw component will cross slip, and that will lead to both uh, multiplication by Frank Reed mechanism as well as formation of dislocation tangles and locks and jogs, kinks. So all this will occur. Kings, of course, are immobile, so they are also a form of major obstacle. And because of all this obstacle creation, the mobility of dislocations will reduce. You'll have to apply more stresses to make them overcome these obstacles. So we'll have a very high work hardening rate. After that, once you have sufficient density of dislocation, other recovery mechanisms will start to dominate. So one thing is that the stresses are so high that the dislocations uh, will be able to move on different slip on some other slip planes, which initially could not be activated due to lower stresses, but at higher stresses, their CRSS values are being reached, so they will also get activated. So mobility will improve. Along with that, in stage 3, the dislocations, because the density is high, they will start annihilating with each other, which will reduce the density, and they will start forming structures which are much more which have lower energy. They will rearrange in maybe till boundaries or subgrain boundaries which have lower energy, and as a result of these low energy structure formations, the mobility of dislocations will improve because now the tangles are less. You have more definite structures in your material. So because of all of these recovery related phenomena, there it will become easier for the, not exactly easier, but the rate of hardening will decrease because other mechanisms are also have also kicked in. Even though stresses are still high, but the rate of increase is lower. So that is where recovery has started to also dominate stage 3. And at high temperatures, these recovery processes will be slightly different and they will be much more stronger because you have more thermal energy available for annihilation um as well as formation of different structures. Diffusion is easier, so that will also lead to climb mechanism getting activated. So edge dislocations can also uh, overcome obstacles more easily by climbing to a different slip plane. This was all about slipping related phenomena and work hardening behavior in metals. In polycrystals, we'll see what happens in the subsequent class. I will not cover it in this one. Now we will move to the last topic we'll cover in this lecture, which is twinning. Mm. So twinning is can be defined as successive shearing of uniform shearing of successive of atoms on successive planes. So sir has already shown it through some diagrams, very good diagram. So basically what is happening is if you have uh, portion of your material like this, it will tend to shear. Maybe you had it initially like this. Let me draw it properly. You had it like this, and there was a shear force being applied. So what will happen is that because of that, the material will deform in this way, and this region where the uniform shear has occurred is called the twin region. This is the twin. These both are untwinned. This is different from slip. In slip, you just have dislocations which are moving on different slip planes and leading to overall formation of slip steps in the material. But and there you have lattice translations whenever a particular slip event is occurring. But here you are having a uniform value of shear strain in the material when twinning is occurring. So all the atoms move by a very specific value in the twin region, and there's a uniform strain. For example, in FCC it is 0.707, which is quite high. This is in the twin region, and there are multiple characteristics of twins which are all different from that of slip. They are very different mechanisms. Twins are also associated with very specific planes. So, for example, in FCC, it occurs in the 111 plane and in the 112 direction. So atoms move along the 112 direction, but on the 111 plane. And this also causes surface relief, just like slip steps. There is a orientation change which occurs here, which does not occur in case of slipping. So in case of slipping, it's just movement of extra half plane which is taking place. But here the orientation is changing, and the orientation becomes a mirror of the matrix orientation. This is characteristics of twins which helps in identifying twins in materials, especially when you are doing twinning, when you are doing EBSD or TEM, transmission electron microscopy, to be able to know the microstructure and orientation of the different grains and different other uh, defects like twin. So the orientation is a mirror image. Also, twinning is less common compared to slipping because the stress required for slip is much less usually than that required for twinning. But in special cases, and mostly these are cases where slip is difficult, more stresses are required. For example, at lower temperatures where thermal energy is lesser, and uh, in cases of high strain rates where the again due to thermal energy and diffusion being difficult at lower time scales, um, slip is difficult, and therefore twinning can occur. The stresses will become enough for twinning to occur. So in such cases, twinning may dominate, but in general, slip is more common, and more of deformation tends to occur by slip than by twinning. Though the strain associated with twinning is quite high. Also, the mechanism exactly of twin formation is still debatable. The CRSS for twinning is also debatable. We know the general trend that it is not so sensitive to temperature, unlike slip. It is not so sensitive to stresses. So that's why at higher temperature, at lower temperatures and higher strain rates, where slip, the CRSS for slip becomes very high. That for twinning does not change so much, so twinning becomes more favorable compared to slip. So one mechanism which is hypothesized is that the partials have a role to play in the formation of twin. So by the movement of partials over successive planes, initially poles are formed and then twins can form as they stack on as they move on successive plane. So In FCC, it is A by 6 to 1 bar 1 bar. So this is for FCC only, this partial based mechanism. And twinning has been seen to be more favorable in case of in HCPs for plastic deformation, or more prevalent in, and bigger cause of strain in HCPs. So this is mainly because slip in HCP is comparatively difficult. In certain slip systems in HCP are efficient, others are inefficient. So depending on the loading geometry, it can occur. It can happen that the slip uh, on those slip systems is difficult, and therefore it is much more easier for twinning to occur. The stress required for twinning is comparatively lower. So in HCPs, twinning plays a bigger role in deformation. That was the whole summary of the week 5. If you have any doubts, you can let me know. Else we'll move on to discussion of some assignment questions. Uh, let's take a 5-minute break and then we'll start. So let's come back after 5 minutes. You can look at these questions and try to solve if you want. These questions are also available on the shared drive. All of them have been uploaded. Okay, let's resume. Let's solve this assignment. So here we have been given a state of stress. Each strength is given for uniaxial loading, and we have to find out whether it will yield or not mm, for von Mises or octahedral shear stress criteria. So let's do our customary thing first. Hmm. Okay, let's go to the question. Oh, this is our stress state 10, 20, 20 minus 20. We have to calculate the principal stresses. Basically 10 minus lambda 20 0 minus 20 minus lambda 20 0 0 0 5 minus lambda. This determinant equal to 0 will give us the values of lambda. So this is the um, equation for finding out the eigenvalue, which is the same as the principal stress or the eigen equation. So let us simplify it. So one value is lambda equal to 5. Another will be lambda minus 10 into lambda plus 20 equal to 400. So this will be lambda minus 20 into lambda plus 30 0. So 5, 20 and minus 30 kg per mm cube are our principal stresses. Now, sorry, mm square, mass per unit area. Now, one Mises criteria is, let us look at it. So, one Mises criteria is root 2 by 3 sigma ys equal to 1 by 3. So, these are the shear stress. This is the shear stress for uniaxial case. This is on the octahedral plane. And this is the shear stress for our current stress state. So let me write it as sigma 1 summation of sigma 1 minus sigma 2 the whole square. 3 can be cancelled. So if we sum up sigma 1 and sigma 2, so for failure to occur, this should be satisfied. Sorry, it will be the opposite. The value of our this quantity should be more than the that of root 2 into yield strength. So this is equal to yield strength is 60 kg per mm square. So 60 root 2 on the left hand side, and on the right hand side we have sum of let's just make this sum 15 square plus 35 square plus 35 square and square root of it. So this will be equal to, let's calculate. 66.9, and this is equal to, it will be more. Root 2 is 1.4 something. 1.41. 84.8. 84.9. So our calculated uh, octahedral shear plane stress value, shear stress value is less than the one for the uniaxial case. So yielding will not occur. Now let's go to the next question where we have maximum shear stress criteria. So in uniaxial case, the maximum shear stress is sigma ys by 2, we know, which is equal to 30 kg per mm square, while the maximum shear stress we have here is, let's see, it will be modulus of minus 30 minus 5 by 2, right? Which is about 17.5, which is less than the case for uniaxial, less than the case for maximum shear stress in uniaxial, which will cause yielding. So here also we do not expect yielding, no yielding. Now let's see the answer. Yeah, let's move to the next question. So if it does not exhibit yielding according to von Mises yield criteria, then what is the factor of safety associated with it? So we have seen it did not yield, right? So what can be considered as the factor of safety if the current stress state is the load it was designed for? So we can say that if it had if it experienced this value of 66.9, as we can call this the composite stress value, which we calculated using this equation, or let's just use 66.9 by 3 as the shear stress value on the octahedral plane for our current stress state, and the one which will cause yielding was 84.9 by 3. Sorry, yeah, by 3. So if we want to know the factor of safety, it will be the currently experienced load divided by the maximum permissible load, maximum load which will cause failure. This is the permissible load, maximum permissible load, and this is the one which will cause failure. So if we do this division, we'll get, sorry, we'll do the inverse of this actually, because factor of safety is the load at which it will fail divided by the maximum permissible load. So equal to 84.9 divided by 66.9. It is 1.27. Let's see the answer. Okay, it's 1.3 here. Maybe during calculations, I didn't look at the mm, decimal points. Well, I rounded it off. Maybe let's just repeat this once. So this is 66.89, 84.85. I'm still getting it as 1.27 only, while an answer is 1.30. So small difference is there. I'll maybe try to look at this later, but I think this is pretty close to the correct answer, so it's fine. Now let's look at the next question. The yield locus for von Mises and Tresca criteria is being compared for a biaxial plane stress condition. The greatest divergence between the two criteria occurs when are the two diverging the most? So if we just look at it, they are having the same value at all of these points. There is no divergence at these points. At other points, the Tresca is giving a smaller surface compared to one Mises. And I think in these regions, it is the highest, right? So for sigma 1 equal to sigma 2, it is 0. Sigma 1 more than 0, sigma 2 equal to 0. It will be 0. So this was the first. Second, sigma 2 more than 0 and sigma 1 equal to 0. Third option, here also it's 0. But sigma 1 equal to minus sigma 2 is are these locations. So here you have a divergence. And based on the answer, you can say that the fourth option is the correct one because here you will have significant divergence. So let's just check. Yeah, it's the fourth option. Mhm. Question number 5. Which of the following statements is incorrect? Polymers exhibit different yield behavior as compared to metals and ceramics because of their different arrangement or bonding. This is true. Polymers behave differently under temperature, tension and compression. As well, the mechanism is different. So it is correct. I'll just try to test true. Yielding of polymers is significantly influenced by hydrostatic pressure exhibited on it. This is also true. Polymers are also affected by the hydrostatic pressure as well as the shear pressure. A plane whose normal vector makes equal angles with each of the principal axes are called octahedral planes. Yes, we have already seen it is about 54.4 degrees. That is the definition of octahedral plane. In metals and ceramics, hydrostatic stress has no role in yielding. Hmm. We have seen that in metals and that in ceramics especially, where you do not have plastic deformation, it's mostly brittle. The breaking of the bond is the cause of failure, and there the normal stresses are what cause yielding. So hydrostatic stress has a role to play. So this is false. Oh no. Okay. This is false. Slip occurs preferentially on close packed planes which are farthest apart. This also we have seen. So slip occurs on widely spaced planes because the width of the dislocation or the distorted region is the highest in these planes. So because the distortion is more delocalized, more diffused, it is easier for dislocation to move on those planes. So slip occurs there. This is true. Slip in BCC crystals is easier as compared to FCC and HCP. This is false. Um, because in BCC the slip system is not as efficient as at FCC. FCC CRSS is lower, slow. FCC in FCC slip is easier. So this is false. The yield strength is lower for HCP as a result. Now let's look at answer. I think we got one of them wrong. Yeah. So the fourth option is actually true as per the answer key. And if we look at it again, then we'll see that yeah, that's correct. Because we did not look at this word yielding. If the question was about fracture, then hydrostatic stress would have caused fracture, but yielding is caused only by plastic deformation. So yielding basically means that plasticity has started. It's the onset of plasticity. So in plastic deformation, we know hydrostatic stress plays no role in case of um, in case of um, uh, crystals, in case of ordered crystals, not necessarily ordered, but crystal lattices where we have deformation. That is not what it is for polymers, where you have a definite arrangement of atoms. So there yielding only occurs by plastic deformation. Sorry, yielding only occurs due to shear stresses, that is slip of atoms. Uh, so this will be true. Hydrostatic stress will not play a role. Next question. A single crystal of aluminium is deformed in tension in 112 direction. Schmidt factor is given below for different slip systems. Which slip system will be activated first? Okay. So for the same family of slip systems, we have been given different Schmidt factor values. Is the 111 slip plane and 1011 slip direction family. Different Schmidt factors are given. We have been asked which will activate the first. Let's look at what Schmidt factor is and what Schmidt law tells about this. This was question number 6. So Schmidt's law is sigma ys equal to m times tau CRSS, where m is your Schmidt factor. So if m is higher, M is based on the geometry of the slip system and the loading direction. What is the relation between them? So higher M implies, because yield strength is same for any material, it will not depend on the orientation. Especially here we are considering polycrystal. Sorry, here we are considering single crystals. Okay. Okay, here we are considering single crystal. So we cannot use this. It will be better to just use the resolved shear stress tau RSS equal to sigma into cos lambda cos phi. This is 1 by m. So this will become equal to sigma by m. Higher the value of m, lower will be the tau RSS. Sorry, this is wrong. Mm, yeah, this is wrong. I have written it incorrectly. Higher Schmidt factor corresponds to higher resolved shear stresses. This is M actually. So tau RSS for the slip system, resolved shear stress equal to applied stress into the Schmidt factor. And then I think this equation is also not correct. Hmm. Here we have been given the value of Schmidt factor directly. So we know that okay, we know that sigma is fixed and will depend on the slip system. And the higher the M, the higher will be the resolved shear stress. So, and the one which will, the slip system for which the resolved shear stress is more than the critical resolved shear stress, that will get activated. And because all of these belong to the same family of, to the same slip system or family of slip systems, the tau CRSS will be the same for all of them. So we just have to see which will have the highest RSS that is most likely to get activated. And that will be root 6 by 61. So that is option C, right? I hope this is clear. Now let's go to the next question. If CRSS is 50 megapascal, what is the minimum tensile stress required at which the material will start to deform plastically? So here CRSS has been given. We are asked what is the tensile stress which will have to be applied for plastic deformation. We know m is equal to root 6 by 6. That is 1 by root 6. M equal to 1 by root 6. And sigma is equal to tau CRSS. Yield strength will be tau CRSS by M. So this will be equal to 50 megapascal divided by 1 by root 6, which is 122.5 megapascal. It's yeah, it's within the limits. Let's move to the next question. So the statement is easy movement of dislocations to a relatively large distance without encountering barriers. We have to, okay, comment on these statements. So let's look at question 8. Which of the above statements belongs to stage 1 of a generic work hardening curve for a FCC single crystal? Stage 1 for a FCC crystal, single crystal. Hmm. Let's see. Easy movement of dislocations to relatively large distances without encountering barriers. Yeah, that's stage 1. Easy glide due to very few mobile dislocations and less obstacles. In second, increased formation of lower quartile barriers with increasing strain. So locks have started to form due to cross slipping and dislocation. Some portions of dislocations getting stuck while cross slipping. So this will be stage 2, activation of cross slip. So activation of cross slip, it occurs during stage 1, stage 2, and it also takes place in stage 3, but we'll call it stage 2. Formation of sessile dislocations. Sessiles are immobile dislocations. They form in stage 2 itself and act as barriers. Escape of dislocations from dislocation pileups and thus reducing of internal stress. So pileup escape can happen at higher stresses because other slip systems get activated. CRSS of those slip systems gets overcome. Stresses are high enough, and also other mechanisms. Mm, Also, the dislocation densities are very high. So majorly other slip systems get activated. That's the, I think, reason for this. So that happens in stage 3. Formation of dislocation tangles, stage 2. These are obstacles which are forming due to multiplication of dislocations and they are cross slipping on different planes. As a result, they form jogs and kinks due to interaction. So stage 1 was S1, stage 2 was S2, S3, S4, and S6. 2, 3, 4, 6. Stage 3 was S5. Now let's look at the answers. What was our accuracy in answering? This is correct. Here we have made a mistake. Here also there's one we missed. So S3 according to it is in stage 3. So they are saying cross slip occurs in stage 3. Hmm, I see. So cross slip I think this is a bit debatable. I just look at Sir's lecture once again related to this. Hmm. Dislocation, multiplication, activation of new slip systems. So that means cross slip. It occurs in stage 2. Stage 3, both uh, recovery as well as strain hardening occur simultaneously. So one part of recovery is cross slip, but I think cross slip occurs in stage 2 also, but in 3 it becomes even more dominant because that is a way for dislocations to escape. We can say that it occurs in 3. It's a dominant mechanism for 3 and not so much for 2. So fine. Now we are correct as per the answer key. Let's look at the next question. What are the 5 independent strains required to meet the boundary compatibility requirement? Hmm. So these last two questions, I have not covered them in the summary course. They are from the last two lectures of the week. So let me start with them in the next lecture, in the next week's discussion session. So these along with week 6 answers will be covered in that. So let's finish this for now. Yeah. Mhm. With this, let's finish the session. Let's close it. We have already discussed the assignments for week 5. Let me also quickly upload it now. In case of any doubts, you can answer. Sorry, you can ask me. I will answer. I'll wait for 5 minutes. Hmm. Hello, there's any question? You have raised your hand. You can unmute and ask. I can't hear you now. You can unmute and ask if you have any question. Or maybe write in the chat. Okay, there's a problem with the mic, I see. You want the previous year's assignment for reference. So in the weekly log sheet, you might have access to that. In the NPTEL portal, you will have the access to weekly log sheet. In that, you have the links for the recorded YouTube weekly doubt sessions, and also the shared folder where all the assignment questions of previous year as well as the selected solutions which I have solved are uploaded. Let me again just give you a link for it. I'll share it on chats. So you can just use this drive to navigate to the assignment folder. You can download all the previous year assignment and try to solve them yourself. If you have any issue, you can look at the solutions which I have uploaded. Mm, just see if you can access. I think you'll be able to access it. I hope that resolves your question. So, um, you let me know if you are able to access the drive link. Okay, thank you. Try to solve the assignment questions. That will give you good practice. So with this, let us close this session. In case you have any doubts, you post it in the discussion forums. There have been some posts. I am happy about it, and I have tried to answer them. So keep posting if you have any doubts. We'll clear it there. Thank you for attending. Goodbye.